Now, what is the photoelectric effect? Well, it involves two things, light and electrons. So, when a certain type of light is illuminated on a metal surface, electrons are emitted. And this was first observed by Heinrich Hertz in 1887. Now, we will be analyzing this um, effect from the perspective of Heinrich Hertz. So, what does Heinrich Hertz know about light? He knows that light is an electromagnetic wave which is established by well-known scientists across the centuries. So Heinrich Hertz is right here. So it's normal for him to analyze this effect based on the electromagnetic theory of light. So for this experiment we need a couple of simple things from the electromagnetic theory of light. So according to that theory, light consists of an electric wave and a magnetic wave perpendicular to each other, and there is the wavelength, and the energy of the electromagnetic wave is proportional to the amplitude squared of the electric field, and the intensity is just the energy per unit time per unit area, and the frequency is the velocity of light over lambda. So the frequency is inversely proportional to the wavelength. So from here we can control a few things. So we can control the intensity, therefore controlling the amplitude, and we can control the wavelength of light, therefore controlling the frequency. Now for the electrons, we need to uh, analyze the motion of it. So electrons are charged particle and they can gain velocity, therefore they can have some kinetic energy. So in order to analyze this, we can just put those electrons in an electric field. So the trajectories of the electrons will be altered by that electric field, and we can control that electric field by setting up two terminals and changing the potential. So this way we can control the potential, therefore we can measure the kinetic energy of the electrons to some extent. So combining these knowledge uh, of the electrons and of the electromagnetic theory of light, we can set up an experiment like this. So there are two terminals capable of creating electric fields, and the light has to be illuminated in one of the terminals, and we can have control over the potential difference. And we plugged in the voltmeter and ammeter to observe the voltage and currents. So let's begin the experiment. So initially I have not applied any voltage, yet the electrons are being emitted from the illuminated metal surface due to the photoelectric effect. And since the electrons are being emitted, we get some current in the emitter. So this is very fine. Now what happens if we increase the voltage a little bit? So notice here that the illuminated metal surface is actually the anode, so some of the electrons will not make into the other side because the electric field is uh, opposing the electrons. and the other terminal it has the similar uh, charge as the electrons. So the similar charge will oppose each other. But some of the electrons still make it because they have the higher kinetic energy than the electric field can produce at this time. What happens if we increase the voltage a little bit further? This time, up to a certain voltage point, all the electrons should stop moving to the other terminal. Therefore, we will not see any current in our emitter. So this is a special voltage value. We call it the stopping potential, which will then be exactly equal to the maximum kinetic energy of the of one of those electrons which barely made it to the other terminal. So we can now gather some data and analyze the effect. So we can set up the intensity wavelength and have a potential range as our input parameters. And what is this metal work function? For now, let's just say it's a metal property. It's equivalent to the changing the metal surface. Like one time I can use gold surface, or another time we can use the silver surface, but I'll go into this later. And we can observe these outputs such as currents and maximum kinetic energy and the time delay. Now I have actually created a MATLAB script to mimic this photoelectric effect, and we can actually observe the results for this study. So for this analysis, for this demonstration, I have inserted these values in my script, and let's see what the observed results look like. Now, the first thing I want to mention here is that for all the photoelectric effects that will be observed, the time delay will look similar to this. It's an extremely small moment, which is of the order of 1 nanosecond, which is almost negligible. So the first observation is that the time it takes the electron to leave this metal surface is almost instantaneous, which contradicts the classical electromagnetic wave uh, point of view, in where electrons need more time to collect energy, since light is a continuous electromagnetic wave. Now, this is a voltage versus current curve with different intensities of light. So as you can see here, with higher intensities of light, we get larger current initially. Larger current corresponds to the more amount of electron emission from the metal surface. However, as we increase the potential, all of those um, current come to zero at one single point, which is the stopping potential. So intensity is not relying on the uh, so the intensity is not changing the stopping potential. Now, what does it mean not changing the stopping potential? Well, it means that the maximum kinetic energy of the electron remains the same. So we can say that the kinetic energy of the electron is not a function of intensity anymore, which is a violation of the classical point of view. So increasing the light intensity should give the electrons extra kinetic energy, but the observed behavior says it's not the case anymore. Now this is another voltage versus current curve, but this time we are changing the wavelength to see what happens. So in here you can see that the stopping potential changes for different wavelengths. So for lower wavelengths the stopping potential increases. That means the lower wavelength is responsible for uh, generating higher kinetic energy electrons, or in other words we can say that high frequency light creates more energetic electrons. So this is uh, actually the inner energy is now a function of frequency. This matches with Planck's conclusion that was made in 1900, which I will be going into it deep in a little bit later. Now, so the wavelength or frequency changes the electrokinetic energy. So this is a voltage versus frequency curve, and naturally as we are increasing the frequency the stopping potential also increases. But as we decrease the frequency there is a certain point where the stopping potential is no longer required because there is no current to begin with. So there is a minimum amount of minimum value of frequency required for the photoelectric effect to even take place. So this minimum frequency is correspond does correspond to a minimum energy. So this is a function of a minimum frequency. This minimum energy is actually the metal work function that we have placed the one of the parameters in the table. So the minimum frequency is required for the photoelectric effect to happen. Now let's take another point right here, and in this point the total energy should be equal to the minimum energy and some amount of and the maximum kinetic energy of the electrons. So let's work with this equation now and replace the energies as a function of frequencies and the maximum kinetic energy as EV naught as we have showed earlier. Now by this time Max Planck has uh, developed a hypothesis in 1900 based on the blackbody radiation spectrum, and then he concluded that light is a discrete packet of energy, and from there he has formulated E equals h nu, where h is Planck's constant, and using that theory Albert Einstein in 1905 plugged it into this equation, and he has formed uh, the equation, or yes, the equation of the photoelectric effect. Now this is what Einstein has done, which achieved him a Nobel Prize. So this is a worked out example. I will just skip it for now. So thank you very much for your time and patience.